Is it working now? Hello? हाँ सर, अब मेरा आवाज ठीक से आ रहा है? मेरा इंटरनेट इंटरनेट से नहीं, मेरा इधर ठीक है, स्टेबल है। आई थिंक बीच में ठीक है। आई थिंक अगर हम बैंडविड्थ को कम करना चाहते हैं तो आई थिंक वीडियो टर्न ऑफ कर ले जब तक मैं ये दूं, देन अगेन Q&A की तरफ अगेन वी कैन टर्न ऑन द वीडियो, है ना? दैट इज पॉसिबल।
नहीं,
आप
आप
कैसे सोचे?
रहिए सर, अब देखेंगे, अगर होगा बीच में तो
श्योर
आप
श्योर,
मिलिएगा। हाँ,
ठीक है ठीक है ठीक है, ओके ओके ओके। Anyway, good morning, sir. Professor Das, I know you. And sorry that I was not, I cannot connect, be there in person. The conference था उसीलिए मेरे को आना पड़ा. But anyway, I'm happy to deliver the talk and
सो
would love to उधर रह के अगर इंटरेक्ट कर पाते बच्चों के साथ.
मैं आपको सर आपके बारे में बच्चों को बताता हूँ, फिर आप स्टार्ट कर दीजिए तुरंत, बिल्कुल।
Sure.
हाँ, चलिए तो एक बार जोरदार तालियों के साथ आज के हमारे मुख्य वक्ता, सर तालियों की गड़गड़ाहट है, माइक्रोफोन ना होने के कारण आपको आवाज नहीं पहुंच पा रही होगी, बट वी आर वेरी हैप्पी दैट कि आप सर इतने व्यस्तम शेड्यूल, सर आईआईटी इंदौर के डिपार्टमेंट ऑफ स्पेस साइंस एंड इंजीनियरिंग डिपार्टमेंट के एचओडी हैं, और उससे कमाल के एक साइंटिस्ट हैं जो अपनी फील्ड में इंटरनेशनली रिनाउंड हैं, बहुत क्रिएटिवली, बहुत लीडरशिप क्वालिटी के साथ न्यू वेंचर्स को ही इज ट्राइंग टू एस्टैब्लिश इन वेरियस पार्ट्स ऑफ आवर कंट्री एंड स्पेशली लीडिंग फ्रॉम आईआईटी इंदौर। और आपको ये जान के बड़ा और ज्यादा प्रेरणा मिलेगी कि सर ने जब हमारे इस निमंत्रण को एक्सेप्ट किया था, उस समय सर अबाउट टू लीव टू ऑस्ट्रेलिया उनके किसी कॉन्फ्रेंस के कारण, जैसे उन्होंने जिक्र किया, सर अभी सिडनी से हमारे साथ जुड़े हैं। तो सर बहुत बहुत स्वागत है राष्ट्रीय अंतरिक्ष दिवस के इस दूसरे मौके पर, और हमसे जुड़कर बच्चों से मुखातिब होकर अंतरिक्ष के बारे में आप बात करने के लिए। एक बार रीजनल साइंस सेंटर भोपाल, जो कि नेशनल काउंसिल ऑफ साइंस म्यूजियम्स की एक यूनिट है, हमारे पूरे परिवार की तरफ से, बच्चों के, विद्यार्थियों की तरफ से, सबकी तरफ से आपका बहुत बहुत स्वागत है। और ये डिजिटली वर्चुअल मंच अब आपका है सर। थैंक यू, प्लीज गो अहेड सर। थैंक यू।
नमस्कार, बहुत बहुत धन्यवाद मेरे को इधर मौका देने के लिए, इंटरेक्शन के लिए। तो मेरा टॉक, आई थॉट कि इट्स अ वेरी इम्पोर्टेंट टाइम फॉर इंडिया। ये आप जानते होंगे कि अगस्त 23 डिसाइड किया गया कि स्पेस डे सेलिब्रेट किया जाएगा आफ्टर टू कोमेमोरेट द इंडियन चंद्रयान 3 लैंडिंग इन द शिव शक्ति पॉइंट। एंड ये एक अवसर है हम लोग पूरे इंडिया में लेते हैं, जहाँ जहाँ भी एस्ट्रोनॉमी स्पेस साइंस का डिपार्टमेंट्स है या सेंटर्स हैं, कि इसमें और भी बच्चों को कैसे एस्ट्रोनॉमी स्पेस साइंस में लाया जाए, नॉट ओनली फ्रॉम साइंस बैकग्राउंड बट ऑल्सो फ्रॉम इंजीनियरिंग बैकग्राउंड एंड वेरियस अदर प्लेसेस। तो मेरा ये प्रयास है कि जो मैं टॉक देने जा रहा हूँ मेनली इंग्लिश में है, लेकिन अगर आपको कभी दुविधा हो, आई थिंक Q&A की तरफ हम उसका एक्सप्लेनेशन दे सकते हैं। एंड मेरा ये प्रयास रहेगा अगले 30 से 40 मिनट तक कि किस क्या क्या मेजर ब्रेक थ्रूज अभी हो रहे हैं एस्ट्रोनॉमी स्पेस साइंस में, अपॉर्चुनिटीज क्या क्या है, उससे थोड़ा आपको जानकारी देने के लिए। तो दैट विल बी माय काइंड ऑफ एजेंडा फॉर दिस पर्टिकुलर टॉक। सो या, सो पहला जो फर्स्ट पार्ट है, आई विल टॉक अबाउट द नियरेस्ट स्टार टू अस, जो कि इज आवर ओन सन। ओके, सन बहुत ही एक, इट्स अ वेरी वेरी और नियरेस्ट स्टार। our entire life, the reason for us being here depends majorly on the location between sun and the earth. ये जो distance है, ये जो the earth has its own magnetic field, उसके वजह से there is a lot of shielding. Sun is volatile, कभी कभी quiet रहते हैं, but there is also a lot of activity from the sun which gets rise to something called solar wind, coronal mass ejection, several disruptive events. जो कि कभी कभी इट इज डायरेक्टेड टुवर्ड्स द अर्थ। तो ये अर्थ तक पहुंचने से पहले गेट्स डिस्ट्रीब्यूटेड एंड डिफ्यूज बिकॉज ऑफ दिस अर्थ हैविंग पर्टिकुलरली अ मैग्नेटिक फील्ड। एंड उसके वजह से जो लाइंस अब दिख रहे हैं वो मैग्नेटिक फील्ड लाइन से विच इज शील्डिंग अस फ्रॉम द सोलर इवेंट्स। ओके, तो इट्स वेरी इंपॉर्टेंट एंड अब इसका जानकारी आपको भी है। यू मस्ट हैव हर्ड अबाउट ऑरोरा, जो नॉर्थ एंड साउथ पोल में है, जो दिखता है जब सोलर एक्टिविटी अर्थ को हिट करता है। सो द पीपल हु स्टे इन हाई लैटिट्यूड दे आर मोस्टली गेटिंग affected by this, but people who stay in low latitude उनको भी एक इफेक्ट हो रहा है, because nowadays what happens is our life depends not only on so yeah, so this is one of the events like a real coronal mass ejection happening, and solar wind, sorry, is directed towards the earth. आपको दिखाई दे रहा है, this is the animation which is kind of how it this things goes. So आपको लग रहा होगा कि okay fine, the high latitude countries are getting bothered by the space weather, the solar events, that is fine because वो polar पे है, magnetic field lines is coming and meeting to the poles, so they are getting affected. So why we, the country like India, which is mostly equatorial between tropic and equator, why we should be getting bothered? See, there are a lot of this currently the satellites. These are main satellites which are basically launched to study this sun earth system. So events जो भी happening between the sun and the earth, उनको study करने के लिए from the space, there are so many missions which are launched. Mainly, see, you can see the solar probe, the ACE, there's now recently a Parker probe is launched, which is not mentioned here. There is this wind satellite, Themis. There are plenty of satellites, mostly from NASA or ESA. But India also now has a new mission called Aditya L1, which has been launched in the solar Earth, solar Sun L1 point. And that was taking data very recently. So, like this, there are other satellites which in our day-to-day life which matters. Like when you go from your home to a nearest restaurant or movie theater, if you're using Google Map, that is based on navigation satellites, GPS. India has its own Navig satellite. So all those satellites which are helping us to navigate on Earth, on sea, on an air, like all these navigation satellites also help us to in the flights, the aircrafts to find its way from the one point to the other. This is guided by the navigation satellites as well. So all those satellites, then our communication satellites, the television, dish TVs, etc., which are basically satellite connected, they're all somewhere near the geo orbit. So even if we are not a high latitude country, because we depend on those satellites, and the satellites are basically between us and the sun, so the satellites can get affected if there is a very violent solar activity hitting them. They can get fried, they can get disrupted and damaged very badly. So it's of importance to have a handle on the space weather, which is kind of how this environment between the Earth and the sun is getting affected by solar activity or something else. Mainly solar activity, because there are no other sources, what to say, as prominent as sun in between Earth and the sun. So there are several studies and study things. You can see there is 3 of satellites which are launched to understand solar activity. And so that we can give some prediction that how often the sun gets angry, sun becomes violent, and what is the next probability of any such disruptive events coming towards the Earth. This is a very important field of study nowadays. This sun-Earth system is becoming a very important aspects of study. not only outside India, but also within India. And so there are several research groups who are spending time in understanding the sun. So modeling the sun in one end. So you can, can I, check your pointer. Just a second. Yeah, so can you see my mouse, everybody?
Yes, sir.
Yeah, okay. So so some of the efforts is in modeling the sun. So what is the sun doing? Mainly the solar corona, the heliosphere, and how what are the probability of there are many indication whether a sun becoming more active or not. Even before it becomes solar wind, there are evidences of this flux tubes, which is this for the beginning of the CME getting there. There are sunspots and several things which are kind of indications of whether the sun is more active than not. So those modelings are getting done by people who study the physics, solar physics, and internal activities. And then a lot of people are working on how these events propagate from the sun to the earth and how it interacts with the earth's magnetosphere. And finally, how it hits the earth and what is the probability of it hitting where and at what is the impact. Those kind of things are really being done nowadays. So this is some very interesting field which is kind of developing and becoming more and more important. India has not only sent Aditya L1 mission, which I will come to a little bit later, but there is also work going on for National Solar Telescope, which is also being think of proposed. Apart from this sun earth thing, if you come a little bit lower, there is somewhere we have the earth's ionosphere. Now all these satellites which we said, which are rotating around the earth, communication satellite, navigation satellites, defense satellites, and weather satellites, everything, they do communicate back and forth with the ground stations. So the ground stations like this collect the signals from the satellite, and any um, perturbation in the Earth's atmosphere, mainly the ionosphere, actually conducts this kind of transmissions. So if you're working on satellite transmission, even for you, it will be very important to understand what the ionosphere is doing, how it is getting perturbed, or how it is behaving, and how the ionosphere gets perturbed. Also, it gets perturbed because of the solar activities, which is directly coming and hitting the Earth's atmosphere. So over and all, I mean, the solar events not only have effects for the satellites outside, but also affects the atmosphere below and do disrupt it, and which also creates issues in satellite communication and transmissions. This affects our supposedly if we're in a flight, the flight path is defined by many of these navigation satellites. So if it gets disrupted suddenly in between, then the flight path will get a little bit disrupted. There are other mechanisms, but it is not very, as efficient as the satellite navigation. Similarly, for the sea, when you are in a ship, the same ship also gets the navigation signal from satellites, and including us. But for us, if we are in a city, then there are other ways to navigate and go follow the maps, etc., etc. But there is no such map in that sense if you're um, in the sky or in the deep sea. So it gets really affected. There's another point which also gets important. Supposedly, if you have a very strong solar activity hitting, then you have these high tension wires. You must have seen this high tension radio, this electric lines, which are going across maybe outskirts of Bhopal. We see it a lot of time in Indore. And this kind of electric grids sometimes gets bothered by the electromagnetic pulses, which are created because of this sudden huge solar activity. There was a very famous Montreal blackout, which happened because of a very strong solar storm hitting the Northern America, disrupting the whole solar grid for about a couple of days. Think about it. Northern countries means it's cold during winter. In winter time, supposedly, this kind of a power grid is hit and it is down for a couple of days. Many people will be dying because of there is no heating. Okay, so it really creates a very hazardous thing for day-to-day human life. So this whole topic of space weather, which I'm kind of alluding at, is connected to key drivers: solar winds, solar flares, and coronal mass ejections, which is coming directly from the sun and then directed towards the Earth. Okay, and why do we care? Because we need to have this navigation satellite accuracy, GPS, GNSS, aviation communication routing. All this depends on this kind of space weather issues. And then finally, power grid stability and satellite health and orbits are also being, affected because of this particular solar activity. So we can definitely study the sun, which is kind of going on. Sun itself is a very amazing object, cosmic object. There are several layers. The core is at the center, the radiative zone, then the convective zone, photosphere, chromosphere, and the outer part is called corona. Okay. Of course, sun derives its energy from the nuclear fusion, which is happening inside the core, and that releases energy and particles. Then there is, of course, there is a magnetic field lines in the top layer, which is also creating these flux tubes like things, which effectively influences this coronal mass ejection kind of a activity. Solar activities. How do we know that the sun is active or not? There are evidences called this dark spots, called the sunspots. You can, if you see an optical telescope, you can see the reflection of the sun, and you will see there are these black spots. So the increasing number of the black spots, these sunspots, actually makes it stands for more solar activity, and decreasing number of sunspots is lesser solar activity. The sun goes through a cycle of this major activity and the minor activities, and that is called a solar cycle. I will come to that in just next slide. Then there are CMEs, the coronal mass ejection. There are billions of tons of plasma hurled into space with a velocity ranging from 250 to 3,000 kilometers per second. Then there are solar flares, which are electromagnetic radiations hurled in the space. And then finally, there are CIR activities, and which are kind of basic manifestation of the solar activity. Now, sun goes through the stage of hyperactivity and then down to the low activity. So these are basically we are tracking the sunspot cycles. So it's a 11-year cycle. So if you see a peak, that means the sun is at its peak activity, and then it goes down for the low activity or solar minima. So when the activity is high, it's called maxima. When it is low, it is called minima. So the solar maxima to minima and up to the maxima, one whole cycle, kind of roughly gets done with a period of 11 years. So solar physicists, space weather scientists, actually are doing tracking of this sunspot cycles, okay? Because we need to know the sun to great details of accuracy. So that is going on. So this people study this sunspots, and roughly the cycle is 11 years, but you can see that some of these maxima are much more than the other maximas. So that also do some kind of a variations. So when I say modeling, you can see that you can see that this particular cycle, 2025, which is over here, sorry about that, the cycle, if I zoom in from the previous slide to this one, you can see that the blue line is actually the monthly values which are predicted, and actually the black data is the actual data which is coming in from the actual. So it's pretty much kind of the predictions are matching with the actual value. And the people are doing the predictions as the solar cycle, progresses and kind of matches with the models which are created. So there are levels of astronomers, solar physicists who are actually working on understanding the sun and predicting this, how the sun will behave in the future in this cycle. Another aspect of this study is about our own Earth's magnetosphere. We already mentioned that the Earth is one of the planets which has a magnetic field. It makes a lot of differences. So when people ask the question that, are we alone in the universe? Is Earth is the only place where there are intelligent, life? Like we humans are alone and there is nobody else in the universe. So search for the extraterrestrial life is still on. One of the major part of astronomy and space science is to look for other intelligent civilization elsewhere in the universe. So as we know that one of the major impact is that we have atmosphere. The Earth has atmosphere which is not present in other major planets in our solar system. So within our solar system, we are most suitably placed from Sun to Earth, and we are having our own atmosphere. Also, on top of that, we also have a magnetic field, okay, which is actually shielding us from these extreme events directed towards us from the sun. That is one of the major, source of the balance where life is, where atmosphere is maintained in the around the Earth, and life is preserved. I will spend a little bit on the ionosphere. Ionosphere is the layer which is the ionized medium. The ionization happens in the ionosphere because of the solar, UV radiation and X-ray radiation. The ionosphere is divided into few layers, D, E, and F. D being the most lowest layer, just from the above the Earth, and E is the next layer, and F is the further layer, mostly towards the sun. So as we go from D to F, we are going towards the sun direction. Ionosphere is the study of ionosphere is extremely important to maintain this kind of satellite communication, to understand communication across one end of the Earth to another over the horizon. Also, because every electromagnetic radiation which is traveling through the ionosphere gets modified by it. So how the medium is behaving is of extreme importance. So ionospheric study is also one of the very important part of the space physics. We told about that there are several, satellites which are looking into from the space to the sun and the sun-Earth area. India has a lot of solar telescopes built on the Earth, looking towards the sun, both in optical, which is in Uday Solar Observatory, and also there's a proposal for building up a national solar telescope. And but recently, about 2 years back, the Aditya mission was launched in the Earth Sun L1 point, which is the Lagrange point 1. And that has several slew of instruments which are studying the sun, both remote sensing as well as in situ observations. These are several payloads. Remote sensing instruments are this VELC, or the visible emission line coronagraph, which is mainly for corona imaging and spectroscopy. Then SOOT telescope, instrument, which is for photosphere and chromosphere imaging, narrow and broadband. Then SOLEX for X-ray observations. Helios for, again, another X-ray spectrometer, soft and hard, the two bands in the X-ray spectrum. Aditya Solar Wind Particle Experiment, or ASPECT, which is kind of studying solar wind and particle analyzer. This is not remote sensing, this is in situ, so it is actually taking the data while from surrounding. And then PAPA, which is the solar wind particle analyzer electrons and heavier ions with reductions, as well as this magnetometer, which is kind of probing the magnetic field in and around the Aditya L1 satellite. Apart from that, as I showed in that particular slide, there are several other orbiting satellites which are probing the sun. One of the most important one is Parker Solar Probe, launched in 2018, and it is actually studying flyby around the sun and flying very close to the sun and actually probing the outer corona. It's flying very close than any other satellite has ever done. It's a very important project, and if you have any interest, Solar Dynamics Observatory is a very important one. It actually, the data is the best part of this slew of telescopes is that data is public, data is available, and even a school children or a college guys can actually access the data and actually make some study with them. Okay. There are several ground-based ionospheric probes also, which is listed over here. Ionosondes, which are from the vertical sounding, and then GNSS receiver, which is basically receiving signal from GNSS satellites, navigation satellites, and there are radiometers and air glow imagers. Similarly, there are space-based several ionospheric probes which are available. A lot of these telescopes, satellites are again data is public, and you can avail it if you want to study in the ionospheric physics point of view. If you want to study the Earth-based, most of the GPS or GNSS receiver data is public. Some of these other high-value equipments like ionosondes, incoherent scatter data, these are actually kind of proprietary and data may not be publicly available. But of course, if you're interested, people can be connected to people where you can kind of start this kind of research. So just changing gears a little bit and coming to something more from space physics to astronomy. I want to just show you that this is the kind of electromagnetic spectrum. So if you're going from this is in wavelength. So wavelength goes inversely as the frequency. So this is the end where this is the very high frequency, lower in wavelength, and this is the low frequency, higher in wavelength. So the gamma ray and X-ray are kind of fall here. Visible light fall in this particular rainbow band, which is showing here. Infrared is roughly here, and then radio observations are kind of here. Now, as you can see, this line is the opacity. Opacity meaning if opacity is 100%, nothing gets transmitted. If opacity is 0, everything gets transmitted. So this is opaque. 100% opacity means fully opaque. 0% means fully transparent. Okay. So radio waves actually can reach the surface of the Earth, whereas X-ray, gamma ray, ultraviolet light just cannot reach the Earth. Visible light, very minor part, actually can reach the Earth, but again gets bothered by the top of the bottom layer of the atmosphere or the troposphere. The water vapors, the clouds, they bother this transmission and the visible light. So if you want to observe any sky in optical wavelength, you need to have a telescope which you can put on the ground and observe it. But supposedly you need more and more sensitive observations, then you need to put the telescope up in the mountains where the clouds are below it. Okay, so it can avoid the cloud layer and can look at very clear sky without difficulty. For radio, we are actually basically happy to be on the Earth, and most of the band is available from the Earth itself. So most radio telescopes are actually found on the Earth. It doesn't need to go to the mountain top. But again, as the radio waves are becoming smaller and smaller, it is going towards the infrared. The same problem which the visible light faces also occurs, which is the cloud bothers the high frequency observation. So you'll find very high frequency telescopes are kind of built in very top of the mountains, similar to the optical guys. In the lower frequency end of the radio, we have the ionosphere, which has something called a plasma cutoff frequency, and because of which the transmissions cannot reach the ground. So if you have a very ultra low frequency radio telescope, that also has to be flown in the sky. Sorry, above the atmosphere in the space. Most of these gamma ray telescopes, X-ray telescopes, and UV are all already in the space-based domain. What is the most famous optical telescope you came across? The Hubble Space Telescope. Okay, and recently we have this JWST or James Webb Space Telescope, which are all space-based observatories. Okay, recently we have a Euclid mission, which is another big satellite which went up from ESA, European Space Agency. India has its own space observatory called AstroSat. In fact, we are going to celebrate some important milestone of AstroSat over a conference next year. And it has X-ray, it has UV, and those important detectors, which are making very breakthrough observations for the Indian scientists and global. So takeaway point is that if you really want to observe the sky, the whole sky actually manifests itself in different wavelengths, not just one wavelength. For us, the visible light is the only thing our eye is sensitive to. So our eye is also like a telescope. It is sensitive to only the visible spectrum. This is a very narrow spectrum. But there is so many information available in the other parts, which our eye is not sensitive. But the universe is giving away information in different bands. So we need to develop telescopes at different frequencies and different wavelengths to be able to capture those information, because information is key to knowledge. Unless you have the information about that particular source, you don't have a knowledge how the source is behaving. Okay, so that's what the most important point is. We need to observe the sky at multi-wavelength, and for that, multiple telescopes has to be built. So there are several other telescopes, like you can see Fermi, which is the gamma ray telescope. Chandra is the X-ray telescope. Euclid are in this visible infrared band, like James Webb, Roman, Hubble. There are a slew of telescopes which are now operating. Sophia is a stratospheric telescope, just operating from the stratosphere in the infrared band. It's operating from this jumbo 787, Boeing 787 jet. Then comes to this visible infrared is a Rubin telescope, LSST or ELT, very famous telescope. ALMA is operating at a very higher frequency in radio. And then the near-term big radio telescope coming is the Square Kilometer Array, which I will spend a lot of time in next few slides. And India is one of the major collaborator in this. This is a picture very, very readily available on the web of our own galaxy, okay, but projected in a different way. And all these snapshots are for the same galaxy, but you can see they are not representing the same picture. They're not looking similar, identical. Why? Because they're observed at different frequencies. The top one is the lowest frequency, or 408 megahertz. The bottom one is the gamma ray, okay, highest frequency possible. And in every frequency in between, or every wavelength in between, it is showing us different images. Why? Because the physical processes which are taking place in the galaxy is different from each other. So at one place, like atomic hydrogen, this is representing just the atomic hydrogen spin flip transitions, which is actually having the wavelength of 1.4 gigahertz. So whatever that is saying to us is visible from here, evident from here. Whereas if you go to molecular hydrogen, the molecular hydrogen emission becomes peak at this frequency, which is much higher. And that is showing us here. At infrared, you see dust. Okay, and gamma ray, you see other stuff. Optical, you see mostly UV radiation. And those are the different changes. So if you really want to create the full information of our own galaxy, just looking at one particular wavelength is not sufficient. You need to know all all the wavelength information before you make out what is our actual galaxy doing, or what is it made up of, what is it evolving to, etc., etc. Otherwise, if you just have a partial information, it will be the same story. You must have heard that 7 blind men looking at that elephant, one touching the feet, it is saying it's a trunk, one touching the tail, it is saying this is elephant is like a snake, like those. Okay, so we will be misinformed and we will be misinterpreting the whole subject. So take home point is the universe is manifesting itself at different wavelengths. Very important to observe it at different wavelengths, which is doing. If you want to do the space telescope, you have to also do the radio telescope, etc., to actually combine the information, and then we will have the complete knowledge of the universe. Great. So STEM is this next slide, which is the M31 is one of the galaxies, which and you can see that this is the H1 image of the galaxy, it's a spiral galaxy like our Milky Way, and the different other like the X-ray, the UV, optical HST image is beautiful, and there's a more beautiful image coming out from the JWST now. So you should look it up on the web, it's available. And so only if you can make the combination of all these pictures, you understand the source much better. The other thing is the size. Okay, when we're looking at the Earth, we are looking at 6,000 kilometers is the radius. When we're looking at a galaxy cluster, which is much more, billion times more larger than these features. Okay, we talk about in megaparsec. Remember, Earth is in how much? In 6,000 kilometers is the radius, right? The size of a galaxy is few hundred kiloparsec. That means a parsec is 10 to the power 16 meter. Okay. So, and the kiloparsec is 10 to the power 19. And few hundred kiloparsec is 10 to the 21 meter. And Earth is 10 to the power 5 meter, roughly, give or take, of the order of magnitude. So a galaxy is so much time larger in size than the Earth. Earth is not even a fraction of the mass of the sun. And in galaxy, we are talking about millions of stars, so millions of solar masses. Okay, there is the galaxy. So that's how the whole thing scales. So if I zoom out from the Earth to the solar system, to the Milky Way, then finally the local group and local supercluster, we're part of a galaxy clusters. If you zoom out, finally, keep going out and out, the model shows your universe looks like these filaments. It almost represents something like a nervous system. Filamentary things and very synapses being the confluence of massive masses where the galaxy clusters form. So if you want to observe the universe, there has to be, again, different scales, different resolutions of telescopes being used to observe this and relate to the bigger picture. So cosmology is basically studying of the universe, how the universe in the bigger picture looks like, the broader frame, not the smaller individual objects, but how the objects are collectively behaving over the period of time is the major tracking for the cosmology people. Okay. But astrophysicists or planetary scientists are looking into individual stars, galaxies, for the planetary scientists, individual planets, and then looking for their features. Another important take-home point, if you want to go home, is that if you're looking for, as science is important, I say, for astronomy and space science, the engineering part is also very important. Why? Because when we are making a telescope, we have to make it the state-of-the-art telescope. It has to be able to detect very faintest of the signals. Okay, I can tell you this lights from the stars, which are distant away, are very fainter than any of your flashlights or any of your cell phone signals. They can easily, they're 1 billionth time fainter than the strongest signal you receive from the sun. So it is very important to make telescopes which can detect these faintest signals with very high accuracy. So you need engineers to perform that. So astronomy actually is a confluence of, science and engineering. The debate which keeps on going in the Indian context is that we are different, but no, that there has to be a confluence of science and engineering to go ahead and do something great. And that's what I'm not saying astronomy is the only field. I may be biased because I am one, but there are other fields also where this confluence is necessary. So it's very important to shred off those boundaries and work together. If you are a scientist, you should also know about engineering. If you're an engineer, you should also know the science, which can get done by the instrument you're building. That's the important for the next generation astronomers and any other scientists who want to make a difference. Okay, so now the question is, very important part is, we know that if you make the area larger of a detector, we get more photons. So the photons is like coming the rain, like the raindrops. Okay, I'm collecting light, which is photon. If I make the bucket larger, I get more number of raindrops, I get more signal, correct? So one thing is that if you make the telescope, make it bigger, and the bigger mix gets more light. So you're more and more, sensitive to parental light signal, right? There's also another thing called resolution. Okay, the ability to differentiate between two stars. Supposedly, you are now very familiar because every cell phone you're carrying is now having like this called this kind of very high value camera. Now we are not worried about the frequency, the reception, but we are buying cell phones nowadays based on the pixel, how many megapixel the camera has, right? Young folks. So supposedly we have a single pixel camera with all those pretty pictures, faces over here. I can see what will I get if I take a snapshot of you. I will get a single blob because it's single pixel. The cameraman is moving over there, right? He has a multi-pixel camera, so that will differentiate between you to the next person sitting beside you. Okay, and so that is the resolution, the ability to differentiate between you and the next person sitting beside you. And the resolution comes by this particular formula, the wavelength over the detector size. Now for optical, the wavelength is smaller, so the detector size to make more and more pixels is much smaller requirement to be able to get a sharper image, right? For wavelengths like going to down to radio, the same thing gets, a difficult thing. Okay. So for example, let's do a small thing. So this is the, so visible light 10 to the power -6 meters, and this, radio, we have 1 meter. Okay. So from visible to the radio, we have a 10 to the power 6, but 1 million times bigger wavelength. So to differentiate between the two objects, I need to have a 1 million times bigger, larger detector than the optical one. You understand the point? So that is also another thing you have to understand, that these telescopes have to be built at different wavelengths with different kind of specifications. Now, so for particularly in radio, when we're talking about it, then at a given point, the size of the telescope requirement becomes so large that people do not able to, it's not feasible to make such a larger telescopes. So we resort to something called having multiple telescope with smaller dishes, but having more number of them. It's a very big, useful principle called interferometry. If you are a physics student, you must have read something called Young's double slit experiment. If you haven't yet, maybe you will read soon. If you're in class 11, 12, maybe. And the principle of interferometry is based simply on the same principle of Young's double slit experiment. Okay. Our closest interferometer to us is something in north of Pune. It's called Giant Meter Wave Telescope, radio telescope, and it was built by Professor Govind Swarup, one of the very big pioneer of radio astronomy in India. You should visit it. It's about 80 kilometers north of Pune. If you're going from Indore, it will be on the way between Indore and Pune. From Nashik, if you bend towards Pune, it will be on the Pune-Nashik highway. This is a very big telescope and very highly sophisticated one and a pride of India. that it also received this IEEE, is the Society of Electrical Engineers internationally, and it has only acknowledged few such facilities, including this Marconi's lab, etc., as one of the milestones. And GMRT has received this milestone in the year of 2024, 2021, I guess. Yeah. So it's a massive work. It's run by National Center for Radio Astrophysics, run by TIFR, and Professor Govind Swarup, the father of Indian radio astronomy, actually built it. And this led to the what is coming next, which is our India's involvement in something called the Square Kilometer Array, which is the next big telescope which is coming up front. This is the again another slide showing the radio telescopes, the ALMA, all the massive instruments across the wavelength band. If you are coming to higher and higher frequency, you have Athena in the you have, of course, radio in X-ray. XKE is one of the radio telescope coming up. You have Roman telescope, ELT, extremely large telescope in optical. JWST already launched. There is things like Astrosat 1 and proposed to be 2 there. And then finally, if you go to up, there's something called Gamma Ray Observatory called Cherenkov Telescope Array, which is also India is one of the member of that. And then finally, you go to the laser gravitational wave detectors called LIGO, and India has one of the LIGO detectors, one of the 3 detectors is in India and the other 2 in US. So all those are the really cutting edge things. If you want to work with LIGO, IUCAA Pune is one of the major science, support for LIGO, and RRCAT Indore is the major institute which are building the instrument for LIGO detectors. For SKA and CRA Pune is the major nodal agency, but IIT Indore also is the founding a consortium member of the SK India. And if you have any questions regarding SK, please write back to me and we can be helped to help. There was a third telescope called TMT, the 30-meter class telescope. It was supposed to be built in Hawaii, and IIA, Indian Institute of Astrophysics, Bengaluru, is one nodal agency for that. However, because of some reason, its future is a little bit uncertain at this particular stage because of the land issue in Hawaii. So we are talking about this SKA, the Square Kilometer Array. It was when I first joined my PhD, 2024, I was hearing that it was going to 2004. I was hearing that SK will be built one day. And when I graduated and became a professor in IIT Indore, I was still hearing it will be done at some day. But now it's actually becoming a reality. It started constructions last year. And this year we have the first images made from the Square Kilometer Array. And so it's very much in progress. Please look out for this. It's a very international project, made out of so many countries where India is one of the members. And India's involvement in SK was sanctioned by cabinet back one and a half year back. And so this is like a telescope spanning over 3 continents. And the mid part, the higher frequency is going to be made in South Africa. Lower frequency one will be in Western Australia, and the headquarters will be in UK, Georgian Bank near Manchester. And all other countries are actually are contributing to this and contributing in terms of manpower, developing softwares. India is majorly developing softwares for running these instruments and also participating in building some of them as time goes. So the low part of the antenna is built in Western Australia, a little bit away from Sydney, is in the eastern coast. The western coast is Perth. So this one is near Perth. And SK Mid is very much near Cape Town, near South Africa. It's a bit northeast of Cape Town, near something called Karoo Desert. So I'm running short of time, so I'm moving very quickly. So if you are astronomy interested, definitely this is a telescope to be looked for. If you are not astronomy interested, you're interested in aspect of it, this is still a very big project for people like you. Why? Because the data rate of these things are massive. It produces terabytes of data in the blink of an eye, these telescopes. So to curate the data, to transfer the data, to make meaning out of the data is a big challenge. It's mostly non-astronomical. It has to link with something called data science, data mining, big data analytics, AI, etc., etc. So if you are an AI enthusiast, this is a field which is developing for you, because it is not possible for astronomers to now individually look into each of the images and understand and infer from it. It has to be somehow coded with AI, ML, machine learning, and AI to be able to make sense of all these things. So it's a big field unfolding for you. And if you are interested, again, we can talk more. The backbone of these telescopes is the linking the data. As I said, data is huge, and it connects from the telescope sites as South Africa and Australia back to member countries like China, India, Europe, and Canada, which are the member countries, as well as Japan. So a lot of work will be going on in this SRC, which are mainly data centers, but data will be geographically distributed. So one copy of data will be available in multiple countries, one copy of every observations in some sense. There are several science working groups which are catering to this. There are several science aspects starting to link from gravitational waves to cosmology, to space weather, to solar science, you name it, and it is here. This is the next biggest thing in the radio activity, like JWST in the visible and near infrared. We work mainly for the cosmology aspect, just to give you a glimpse. So this is the whole structure formation history of the universe. We start from Big Bang, where we suddenly something came out of nowhere and the universe started happening. It expanded, and a lot of other things happened before it came to this particular stage where we see some photons are leaking out of this initial phase and propagating out. Universe is expanding, becoming neutral, decombining, and then waiting for it
Sir,
to
we'll take few
again.
questions at the end after your talk. बच्चे बहुत हैं तो आपके कुछ सवाल लेंगे सर आपके उससे जब आप फिनिश कर देंगे. Thank you.
Sure. I will just wrap up in 5 minutes. Okay. Yeah. So this whole universe became neutral, and then finally the first stars and galaxies formed, and then finally it evolved to the present day galaxy and stars. So this whole study of this thing is basically cosmology, and people have found evidence of the cosmic microwave background, which is the surface of blast scattering. But people are still studying these early epochs of the star formation, primary stars, the first stars that formed, and then studying how it evolved to the current day stars and galaxy. We skip this. So these pretty pictures are basically for a galaxy cluster, and we don't have much time to talk about today. You must have heard about something called Event Horizon Telescope, which is kind of another big thing, which is connecting all the telescopes across the globe and getting the highest resolution possible to able to image first the black hole, which is the center of M87, the nearby galaxy, and then finally our own supermassive black hole, center of our own galaxy, has been done by this EHT. So there is next generation EHT also being planned, and look out for those. Before finishing, I must touch about two things which are very near and dear. One is this recent launch of this something called NASA ISRO synthetic aperture radar, which is the NISA, and it has this fantastic boomed reflector telescope, which is actually looking back. It's not doing astronomy; it's doing purely geophysics, geo observations, looking for similar to interferometry. SAR is another kind of interferometry, which is done. And there's the L band, which is 1.4 gigahertz, and S band, which is about 2 gigahertz to 4 gigahertz bands, in which this operates, NISA operates, and it does something like a mapping of the Earth in and taking synthetic aperture radar images from here, which is just launched and it will be operational. So again, another important area where you guys can contribute and join. Coming up is this Moon Earth mission. So there is a slew of missions from NASA is happening in Artemis missions 1, 2, 3, and finally the idea is to land human aligned to finally go from a unmanned mission to a manned flight in our Gaganyaan, made solely by India. So with that, I thank for your patience and sorry for the initial few minutes of disruption of the. Fine. Over to you, Dr. Saket. Yeah, thank you for the opportunity.
थैंक यू सो मच फॉर वंडरफुल टॉक सर। अब चाहें तो आप टॉक को एंड कर सकते हैं ताकि आप विजुअली हम आपकी स्क्रीन को ले लेंगे। जी हाँ, थैंक यू। एक बार जोरदार तालियों के साथ इस शानदार टॉक के लिए। और ये बड़ा इंपॉर्टेंट ओकेजन है जब हम पूरे भारत में भारत के अंतरिक्ष यात्रा की जो गाथा है, एस्ट्रोनॉमिकल इंस्ट्रूमेंट्स, अगर हम आज इतना एडवांस निसार की बात कर रहे हैं आप सर, क्योंकि आपके एक बहुत नियर एंड डियर है वन ऑफ द प्रोजेक्ट्स ऑफ निसार। एक्चुअल में इसरो की बहुत उसमें पर्सनल कहानी भी इन्वॉल्व है। सैक अहमदाबाद का भी बड़ा रोल है निसार के कैस बैंड में, और एल बैंड इज प्रोवाइडेड बाय नासा। इट्स इंटरेस्टिंग, इस निसार के ऊपर भी हमारे इस प्रदर्शनी में जिसका उद्घाटन आज सुबह हुआ है जिक्र है। तो एंशियंट इंस्ट्रूमेंट से लेकर हम चाहे शंकु यंत्र की बात करें, सनडायल्स की बात करें, जंतर मंतर पे जो सम्राट यंत्र बनाए गए थे राजा सवाई जय सिंह द्वितीय के द्वारा, उनका जिक्र यहाँ पर है। सामंता जी का उड़ीसा में जो कंट्रीब्यूशन है वो जो सेलेस्टियल मेजरमेंट का उसका जिक्र है। केरला स्कूल ऑफ एस्ट्रोनॉमी की बात हो रही है, फिर आर्यभट्टा भास्करा, और फिर भारत का खुद का पहला सैटेलाइट आर्यभट्टा, और हमारे इसरो की जर्नी। और सबसे कंटेम्पररी एंड ग्लोबल पर्सपेक्टिव में सर आपकी टॉक ने आज इस द्वितीय राष्ट्रीय अंतरिक्ष दिवस को और खास बना दिया कि आपने रिसेंट ट्रेंड्स इन एस्ट्रोनॉमी और स्पेस की जो बात की। तो जो ऑडियंस है अभी इस सभागार में, उनके लिए तो है ही, साथ में जो लाइव ऑडियंस हमारे यूट्यूब चैनल पे इस प्रोग्राम को देख रही है या इस कंटेंट को बाद में कंज्यूम करेगी, तो एक वैल्यूएबल रिसोर्स क्रिएट हुआ है फॉर देयर लेवल ऑफ अंडरस्टैंडिंग इन द फील्ड ऑफ स्पेस साइंस एंड टेक्नोलॉजी। जैसा आपने कहा, ये सिर्फ स्पेस या एस्ट्रोनॉमी में करियर बनाने के लिए बस मात्र नहीं है। अब जिस भी फील्ड में आगे जाएंगे, यू विल कम टू नो अबाउट इंडियाज कंट्रीब्यूशन, एंड दैट विल आल्सो गिव यू अ रे ऑफ होप कि आप बेहतर और बहुत कुछ बड़ा कर सकते हैं। भारत जिस तरीके से आज दुनिया में अपना योगदान दे रहा है, और आपके इस विशेष योगदान के लिए प्रोफेसर अभिरूप दत्ता सर, वी आर वेरी मच थैंकफुल टू यू। आप आंचलिक विज्ञान केंद्र भोपाल के साथ हमेशा बने रहते हैं और हमेशा चाहते हैं कि हम कुछ नया करें आपके साथ मिलके। तो आपका लीडरशिप में जो आईआईटी इंदौर में जो डिपार्टमेंट एक फ्रंट लीड कर रहा है इंडिया में ग्लोबल स्टेज पर, उसके लिए भी एक बार जोरदार तालियां हमारी सभागार की ऑडियंस से। और चूंकि आप एस्ट्रोनॉमर हैं और कहीं एस्ट्रोनॉमी का मेरे अंदर भी बड़ा इंटरेस्ट रहता है, तो मैं आपको ये बताना चाहूंगा कि एस्ट्रोनॉमी में नॉर्दर्न एंड सादर्न हेमिस्फीयर बहुत मैटर करता है नाइट स्काई में। आप अभी ऑस्ट्रेलिया में हैं, सिडनी में हैं वर्तमान में, सीधा प्रसारण टेक्नोलॉजी की एज देखिए, आप जुड़े हुए हैं हमसे। पृथ्वी के दक्षिणी गोलार्ध के ऑस्ट्रेलिया वाले शहर का जो स्काई है ऑस्ट्रेलिया कंट्री के ऊपर, वो हमारा स्काई नहीं होता है, तो सदर्न स्काई होता है। एस्ट्रोनॉमी के लिए बहुत जरूरी होता है। तो आप देखिए, नॉर्दर्न हेमिस्फीयर के साइंस के लोग सदर्न हेमिस्फीयर से यानी कंप्लीट अर्थ के व्यू को कवर करते हुए इस द्वितीय राष्ट्रीय अंतरिक्ष दिवस को मना रहे हैं। इस बात के लिए सर आपको बहुत बहुत धन्यवाद, हमारी नेशनल काउंसिल ऑफ साइंस म्यूजियम्स की तरफ से, हमारी साइंस सेंटर की टीम की तरफ से। और आज हमारे बीच में अभी प्रोफेसर दास तो अभी निकल गए हैं आईसर में उद्घाटन करने के बाद। हमारे बीच में हमारी लोकल एडवाइजरी कमेटी के माननीय सदस्य प्रोफेसर अमिताभ पांडे सर भी हैं, जो इंदिरा गांधी मानव संग्रहालय के डायरेक्टर हैं, और वो हमारी लोकल एडवाइजरी कमेटी के ऑनरेबल मेंबर भी हैं। तो सर ये बड़ा खास और विशेष प्रोग्राम है जो पूरे भारत में सेलिब्रेट हो रहा है। और आप भारत में भौतिक रूप से भले ही ना हो इन चार दीवारियों को बाउंड्री के भीतर, लेकिन आप ऑस्ट्रेलिया से भी उस भाव को कॉन्फ्रेंस में बिजी होने की बात कर रहे हैं, ये काबिल तारीफ है। मैं आपका ज्यादा समय नहीं लूंगा, बहुत बहुत धन्यवाद कहूंगा। और अगर अनुमति हो तो सर सबसे क्रिटिकल कंपोनेंट अगर साइंटिफिक एंडेवर में है, सवाल और सवालों के जवाब। तो अगर अनुमति दें तो 2 या 3 सवाल ले सकते हैं सर।
Sure.
तो अब ये मंच आपके लिए है, आप सवाल पूछना चाहें तो बेझिझक जो भी मन में उस सवाल विषय से रिलेटेड हो या हमारे एग्जीबिशन से रिलेटेड हो, जो आप पूछ सकते हैं कोई भी खगोल विज्ञान हमारे सर के बाद दीजिए, शिक्षक महोदय को दीजिए भाई।
Good afternoon, everybody. And student and each and everything. Professor Datta sir, I am myself B. Bhattacharya from Nalanda School of Excellence, कोलार। मैं ये जानना चाहता हूँ सर, छोटे बच्चे भी है यहाँ पे, जो तारे मरते हैं, डेड होते हैं, वो ब्लैक होल में जाते हैं, तो वो उसके बारे में थोड़ा सा आप बता दे सर, जिससे क्या हो छोटे बच्चे थोड़ा इंस्पायर हो, क्या आगे फ्यूचर में वो इसमें जा पाए, इस लाइन में। थैंक यू।
बड़ा कमाल का सवाल है सर। अब आपके पास है कि हर तारा तो मर के क्या बनता है, आप बताइए सर।
हर तरह मन के ब्लैक होल मतलब देयर इज डिफरेंट फेट्स, इट डिपेंड्स ऑन द मास ऑफ द पर्टिकुलर स्टार, और काफी और चीजें भी है। या कभी कभी स्टेलर मास ब्लैक होल बनते हैं, एंड कभी कभी न्यूट्रॉन स्टार भी बनते हैं। सुपरनोवा क्रिएट होता है डेफिनेटली, एंड ये तो अपने आप में एक पूरा सब्जेक्ट है। तो आई थिंक साकेत सिंह जी विल बी वेरी वेरी appropriate to discuss this in more details with the young people. I think probably, yeah, it's just not one or two questions, but I think it needs a lecture to to attend. But yeah, सारे तारे का फेट या अंतिम दशा सेम नहीं होता है। they definitely end with something called supernova, जो एक मासिव एक्सप्लोशन होता है। उसके बाद कुछ कुछ न्यूट्रॉन स्टार भी बन जाते हैं, कुछ कुछ और कुछ इसमें अवधि में रूपांतरित होते हैं। तो आपका बात बिल्कुल सही है। जैसे हमने अभी बताया आपको कि वो प्रिमिटिव जो स्टार्स थे वो मेटल जीरो स्टार्स थे, वो भी अपना लाइफ साइकिल के बाद एंड में जाके सुपरनोवा बने, एंड देन काफी एक दो राउंड ऑफ दिस साइकिल ऑफ बर्थ ऑफ द स्टार एंड द एंड, उसके बाद मेटल फॉर्मेशन चालू हुआ। ये तो पहले तो मेटल्स नहीं थे। हाँ, तो ये जो मेटल्स अभी जो हम लोग पहनते हैं गोल्ड, इट ऑल्सो रिलेटेड टू एस्ट्रोनॉमी, because it came from the start after evolution of stars, couple of this round birth and death, then only metals started forming, and and then from the stars planets formed, and planets bear these metals in their core, and so we excavated them and then we started making it and finally wearing them. So yeah, it's a big topic, but मेरे ख्याल से थोड़ा बहुत मैं I shed some light on that subject, but I think Saket Singh ji will be able to take it forward and make it more
Definitely,
elaborate. Yeah, thank
definitely,
you.
sir. Thank you for that honor. We'll try to satisfy those queries and very critical component for their journey also. हम बात करेंगे क्योंकि
Yeah.
सर का बहुत बहुमूल्य समय है इस कॉन्फ्रेंस में है, तो हम ज्यादा समय नहीं लेंगे। सर एक बार फिर से आपको बहुत बहुत धन्यवाद। आप सर जिस कॉन्फ्रेंस में पूरी तल्लीनता से इंगेज हैं, हम चाहें आप वहाँ सफलता के साथ लौटें आपके पार्टिसिपेशन से, और हमारे यूथ जो
Thank
आगे
you.
आके पढ़ने वाला है आईटीज में रिसर्च में आपसे इंस्पायर होता रहे। ऑन दिस नोट, ऑन दिस वेरी स्पेशल ओकेजन, आई एम श्योर कि सर आप इसके बारे में इंटरनेशनल फ्रेटर्निटी को भी बात कर रहे होंगे कि भारत सेलिब्रेट कर रहा है आज 23 अगस्त को, तो जरूर सर हमारा ये इंडियन स्पेस प्रोग्राम की ये जर्नी ग्लोबल है।
Well,
थैंक यू सर, थैंक यू सो
well,
मच।
thank you very much. Thank you. Thank you. No,
जी सर, अब आप
I'm leaving the, huh?
जी सर, थैंक यू, थैंक यू। मैं अपनी ऑनलाइन ऑडियंस को, हाँ जी सर आप कर सकते हैं। मैं अपनी ऑनलाइन ऑडियंस को भी कह सकता हूं कि आप ये कमाल के लेक्चर्स के आप लाइव चैट में भी हमें आप जब लिखते हैं सवाल हम लेंगे, आप कमेंट में भी अपना फीडबैक हमें दें ताकि हम और बेहतर कर सकें इन कार्यक्रमों को, और सब्सक्राइब करना जरूरी है। डिजिटल एज में आप हमें सब्सक्राइब करना भूलें ना हमारे यूट्यूब चैनल को, और एक क्यूआर कोड आपकी स्क्रीन पे दिखाया जाने वाला है, आप उसको फॉलो करने का भी प्रयास कर सकते हैं ताकि साइंस सेंटर की एक्टिविटीज आप तक पहुंच सकेंगी। बहुत बहुत धन्यवाद हमसे इस लाइव स्ट्रीमिंग में जुड़ने के लिए, और इस द्वितीय राष्ट्रीय अंतरिक्ष दिवस के इस ग्रैंड सेलिब्रेशन में जब हमारी काउंसिल पूरे भारत में अपनी विभिन्न विज्ञान केंद्रों में विशेष प्रदर्शनी जिसका नाम है प्राचीन आकाश से आधुनिक क्षितिज तक भारत में अंतरिक्ष विरासत पर प्रदर्शनी प्रदर्शित की जा रही है, आज उसका उद्घाटन प्रातः मॉर्निंग में हमारे विज्ञान केंद्र के प्रांगण के टेम्पररी एग्जीबिशन हॉल में हुआ है, जो आप सबके लिए खुली है। सुबह रोज 9:30 से 6 बजे के बीच में रहने वाली है। आप बिल्कुल जाइए, भारत की प्राचीन यात्रा से लेके आधुनिक अंतरिक्ष अभियानों तक की जानकारी उसमें है। इस नोट पे हम लाइव स्ट्रीमिंग प्रोग्राम को यहाँ समाप्त करते हैं और कार्यक्रम के अंतिम पड़ाव जो कल हमने क्विज किया था, आज हमारे बीच में ऑनरेबल प्रोफेसर अमिताभ पांडे सर हैं, जो कि इंदिरा गांधी मानव संग्रहालय, इंदिरा गांधी राष्ट्रीय मानव संग्रहालय IGRMS के निदेशक महोदय हैं और कमाल की क्यूरियस एक भौतिक शास्त्री भी हैं उसके, और इंडियन इंस्टीट्यूट ऑफ फॉरेस्ट मैनेजमेंट में उनका काफी लंबा समय रहा है। उस अनुभव के साथ साथ वो हमारी आंचलिक विज्ञान केंद्र भोपाल के लोकल एडवाइजरी कमेटी के ऑनरेबल मेंबर भी हैं। सर बहुत बहुत स्वागत है आपका। अब हम वो कार्यक्रम शुरू करेंगे, तो ये लाइव कार्यक्रम को यहाँ हम समाप्त करते हैं। धन्यवाद।